dear students, we had discussed in the last video potential gradient and we had found out the relationship between the electric field and the potential gradient. So E is equal to minus dV upon dr. So we will continue with the same topic in this video also. So first, what is potential gradient? Potential gradient, the electric field intensity at a point in an electric field in a given direction is equal to the negative potential gradient in that direction. So E is equal to minus dV upon dr. Now the SI unit for electric field that we had discussed is from the formula F is equal to Q naught E. So E is equal to F upon Q naught is 1 upon 1 Newton per Coulomb. And from this we have the electric field is equal to volt upon distance, change in voltage upon change in potential upon change in distance, that is volt per meter. So another unit for electric field intensity is volt per meter. 1 Newton per Coulomb is equal to 1 volt per meter. Is it clear? Then we can have two metallic plates. There are two metallic plates having positive charges on one plate and a negative charge on another plate that are separated by the distance d. There are two metallic plates that are having charges, positive charge on one plate and a negative charge on the another plate. They are separated by the distance d, and let the potential here be V1 and V2. So potential difference E electric field can be calculated as V1 minus V2 upon D. The electric field between the two plates, which is in the direction from positive to negative, is given by the formula V1 minus V2 upon D. Is it clear? So electric field is two metallic plates that are having charges positive and negative. The electric field is given by the formula V1 minus V2 upon D, where D is the distance between the two metallic plates. Then we also know that V is equal to 1 upon 4 pi epsilon naught. V is equal to 1 upon 4 pi epsilon naught Q upon R. And from this formula we have E is equal to minus D upon dr. That is in bracket 1 upon 4 pi epsilon naught Q upon R. So what do we get? E is equal to 1 upon 4 pi epsilon naught Q upon R square. So from this potential gradient, if we differentiate potential gradient with respect to distance, we get electric field intensity E. We get the formula for the electric field intensity 1 upon 4 pi epsilon naught Q upon R square. Is it clear? Then another very important thing that I will like you to know is that suppose electric field intensity is in this direction and there are this. Then there are 3 points A, B and C. This is point A, this is point B, this is point C. We have to find out the electric potential in the ascending or descending order. That is, which point will have highest potential, which point will have the least potential. So potential at A is maximum and least is at C. So as we go in the direction of the electric field, as we move in the direction of the electric field, the electric potential keeps on decreasing. Is it clear? If the point is moving towards if the distance is moving towards in the direction of the electric field, then the electric potential is decreasing. So this is VA. VA potential at A will be maximum and potential at C will be least. Okay. The next point is electric potential energy of a system of charges. So we know that there are two or more than two charges, then there will be force of repulsion or attraction acting between these two charges. If they are positive charge, or both of them are negative, then force of repulsion, otherwise force of attraction. So there is certain amount of work done in taking the charge away from each other. If there are two similar kind of charges, then there will be repulsive force. So there is certain amount of work is done in taking away from each other or bringing closer to each other. This work is stored in the form of electrical potential energy. Okay, there is already one Q charge and another charge Q2 is brought near or taken away from it, then certain amount of work is done. This amount of work that is done in bringing that charge Q2 in the presence of charge Q1 is stored in the form of electrical potential energy. So we define the electrical potential energy of a system of charges is the electrical potential energy of the system of charges is the work done in bringing a charge from one point to another point or from infinity to a given point in the system. Okay, what is the electric potential energy of a system of charge is the work that has been done in bringing the charges from infinity to near each other to form the system. Let us have a system of charges. There are two charges Q1 and Q2 that are separated by a distance r. They are at the point A and B respectively. Now initially we take here that there is a vacuum. Whole system of charges is in the vacuum. So the value of K is equal to 1. Okay. Now what we take? We consider the particle Q2 at infinity. And there is only one charge at A, Q1. Okay. So what is the potential due to the charge Q1? What is the potential due to the charge Q1 at the point B? So potential is equal to V equal to 1 upon 4. If we are bringing the charge particle from infinity to a given point. Okay, if we are bringing the charge particle from infinity to a given point, the Q2 which is at infinity, we are bringing it at the point B. The work done is equal to 1 upon 4 pi epsilon naught Q1 upon potential at the point B is equal to 1 upon 4 pi epsilon naught Q1 upon R. Now we know that work done is equal to charge into potential. Work done is equal to charge into potential. So work done is bringing the charge Q2. If we are bringing a test charge, the potential at the point B is equal to 1 upon 4 pi epsilon Q1 upon R. If we are bringing Q2 charge from infinity to the point B, work done is given by the formula Q2V. Work done is equal to 1 upon 4 pi epsilon Q1 Q2 upon R joules. This work done is stored in the form of electric potential energy. So this is denoted by the letter U. U is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R. Is it clear? So in the system of charges, electrical potential energy is given by the formula 1 upon 4 pi epsilon naught Q1 Q2 upon R. Then there are certain important things that are to be told. In the above formula, Q1 and Q2, these are charges. They are always placed along with the sign. So we will put the values of Q1 Q2 along with positive or negative sign. If the signs are multiplication of the sign is positive, then work done is positive. That is, if the charges are similar, then work done is positive. If the charges are unlike charges, then work done will be negative. Is it clear? Then positive value of potential energy indicates net repulsive force acting between the charges. Okay? If plus plus or minus minus, they are similar charges. So what will happen? The repulsive force will be acting between the charges. And if the one of the charges work done is negative, then there is an attractive force. Okay? Then variation of U is inversely proportional to R. Is it clear? Variation of U is inversely proportional to R. That is, its potential energy decreases as the distance between the two charges increases. Okay? As the distance between the two charges increases. Variation of U with distance R between the charges is shown in the here. So now when the system has more than two charges, there are number of charges greater than 2, then the pairs that will be formed will be given by the formula n minus 1 by 2. We determine the potential energy of each pair using the last formula, that is 1 upon 4 pi epsilon naught q1 q2 upon r, and do the summation of the energy due to each pair. So let us see here. We have three charges q1, q2, q1 minus q2 and q3. There are three charges placed, so they are forming a triangle. The distance between q1 and q2 is r12. Distance between minus q2 and q3 is r23. q1 and q3 is r13. Then the energy of this whole system, this is one system, the energy, electrical potential energy of this system is given by the formula U equal to 1 upon 4 pi epsilon naught q1 minus q2 and the distance between the charge r12. Then minus q2 q3 and the distance between the r23. Then plus q1 q3 r13. Okay, so we find out the electrical potential energy due to the two charges or pair of charges, and then sum them up. So that gives out the electrical potential energy due to the system of charges. So my dear student, the next very important point is equipotential surface. I think this has been asked this year in the examination to define electropotential surface, that is equipotential surface. As the word suggests, equipotential means the surface at which the potential is same. Okay, equal potential, the surface at which the potential is same. So any surface over which the electric potential is same everywhere is called an equipotential surface. Okay, so we have a potential surface of a charged body in a space. For example, the surface of a conductor is an equipotential surface. Equipotential surface can be drawn in a space in which there is electric field. Let us consider a charged particle plus q, an isolated charged particle plus q. A plus q is a charged particle, positive charged particle q. It will have a potential around it or an electric field around it. Now, electric field is in all the direction, that is spherical. It will be in all the direction. Here, 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 here. Spherical. That is in all the directions. The charged particle will have electric field in the space around it. Now, we know that the potential is given by the formula V equal to 1 upon 4 pi epsilon naught q upon r. So, at a distance r, we draw a sphere. So, we have drawn a sphere at a distance r from this point charge. What will happen? There is a sphere that is drawn. Now, all the points, according to the formula, all the points over this sphere will have the same potential. So, this sphere becomes a equipotential and equipotential surface. Now, if we take another distance, then another sphere can be drawn, and this again becomes an equipotential surface. Okay, so all the consecutive spheres or concentric spheres that are drawn will form different equipotential surface. So, equipotential surface is the one where the charges, where the electric potential at the surface is same. So, here it will have potential V2, here it will have potential V1. V1 and V2 will be different because the distance is different. But at all the points over this sphere, potential will be V1. Over this surface, at all the points, potential will be V2. Is it clear? Is it clear? Then in the electric field also, when you talk about the electric field, if the electric field is coming out from the plane surface, perpendicular to the surface, at equal distance, if the line of forces of the electric field are coming out perpendicularly from a plane surface, then these plane surfaces are known as equipotential surface. Is it clear? So define equipotential surface. What all points can you give to tell that a given surface is a equipotential surface? Since the surface has got same potential, then potential difference between 2 points on the surface will be 0. That is very important. We take 2 points over the surface A and B. The potential difference will be 0. This is 1 point. Okay. Potential difference between any two given point will be 0. Second, one work done in moving a charged particle from one point to another point over the surface will also be 0. Okay, work done is 0 because there is no change in the potential difference. There is no potential difference or there is no change in the potential. Second, the electric field lines are everywhere at a right angle to the equipotential surface. Okay, the electric line of forces are always perpendicular to the surface, equipotential surface. Because why? Because E is equal to minus dV upon dr, potential gradient. Now, if E is equal to minus dV upon dr, then change in potential will be equal to 0. This means that electric field and hence the line of forces are always perpendicular to the surface. Okay. That is, the electric field and the line of forces are everywhere at right angle to the equipotential surface. This is so because there is no potential gradient along any direction parallel to the surface, and so no electric field parallel to the surface. Electric field parallel to the surface is 0. This means that electric field E and hence the line of forces are always at right angle to the equipotential surface. This will happen only when the component of electric field parallel to the surface is 0. The next important point is there is a family of equipotentials. Now I have drawn number of spheres, 2 spheres we can draw, and more than this in between at a different distance or different radii. This is known as family of equipotential surface. Now if these spheres are very close to each other, then the electric field is stronger. Okay. If the spheres are very close to each other, then the electric field is stronger, and farther apart, then the field is weaker. This is given by the formula dr is inversely proportional to electric field. Okay. So in the diagram, if the spacing between the equipotential surface is less, that means the field is stronger. And if the spacing is more, then the electric field is weaker. Then last important point about equipotential surface is that no two equipotential surfaces can intersect each other. That is, no two equipotential surfaces can intersect each other. Now the reason why. An equipotential surface is always normal to the electric field. If two equipotential surfaces intersect each other, then at the point of intersection, there will be two directions of electric field. Electric field will be in two directions, which is impossible. So both the lines of forces and the equipotential surface can be used to depict the electric field in the space. So that is all about equipotential surface. So this is a very small point, but a very important point that is more often asked in the board examination in 1 or 2 mark objective type questions. So now most of the questions section A are 2 marks. So equipotential surfaces are generally, these kind of questions are generally asked in the exam